Okay, let's go ahead and get started. So today it's our pleasure to have Stephen Moses from Quantinuum. So Stephen did his PhD at JUA at the University of Colorado Boulder under Jun Yi and the late Debbie Jin. He then went to do a postdoc with Chris Monroe at Maryland. This is before all the ion people moved to Duke. He was there for a year and a half or something before
Yeah.
he realized he had to go back to Colorado. And he's been at Quantinuum ever since. And he's going to tell us about scaling trapped ion systems at Quantinuum. Please join me in welcoming Stephen.
Okay. Thanks, Jake, for the kind introduction and for the invitation to speak here today. Let's make sure this is working. Okay. So today I'm going to tell you about the recent work we've done at Quantinuum and scaling trapped ion quantum computers. So I'm currently leading a project that's focused on this racetrack-shaped ion trap, which you may have read about, which is our second generation ion trap. And in this bottom GIF here is just a series of images of ions transporting around this racetrack. There's 32 ions here. And then this picture here is a picture of our grid trap prototype, and I'll kind of explain the motivation for that in a bit. So for those of you not familiar, Quantinuum is a company we're about 2.5 years old now. We formed from the merger of Cambridge Quantum and Honeywell Quantum Solutions. So we used to be part of Honeywell. And as far as I'm aware, we're the largest integrated quantum computing company in the world. So we have around 500 employees in sites around the world. The hardware effort is based in the US, in Colorado and Minnesota, and the physical system, the racetrack system, is actually physically located in Broomfield, which is about halfway between Denver and Boulder. So this chart here I stole from the Quantum Insider that in 2022 made this chart of all the different companies involved in quantum computing. Since I would say in the last decade or so, there's been a realization that to truly scale quantum computers, you're going to need a lot of resources, and those typically available in industry. And so you probably recognize a lot of these companies. The quantum processing units are the companies actually making the quantum computing hardware. That's this part of the chart here. And all the different modalities, superconductors, ion traps, neutral atoms, photonics, are well represented here. And of course, this is a non-exhaustive list, and there are new companies that pop up all the time. So I think this really just sort of shows the explosive growth in the field. And of course, just doing a quick Google search, you can find tons of articles about quantum computing. So there's obviously a lot of excitement and hype in the field. But I'd say that there's still a lot of challenges in quantum computing, and the main one being scalability. And so while all the basic building blocks, such as the single qubit, 2-qubit gate, state preparation, and measurement, have been demonstrated in academia and industry over the last several decades. Truly scaling these systems to have millions of physical qubits with error rates in the 10 to the minus 3 or below some error correction threshold still remains a huge challenge. And so today we're sort of just breaking into this noisy intermediate scale quantum era, and then ideally we want to increase the number of qubits while decreasing error rates. And so today I'd like to tell you about how at Quantinuum we're sort of making progress along those lines, both increasing the number of qubits while also improving error rates. So let me just give a brief outline. So first I'll talk about the architecture that we're using at Quantinuum, which is a so-called quantum charge coupled device. Then I'll talk about our roadmap and kind of the motivation for this racetrack system, talk about the experimental aspects of the H2 system, and then the set of experiments we use to benchmark it. And then I'll talk at the end about a few other projects that we're working on as well. Okay, so why trapped ions and why this quantum charge coupled device architecture? So thinking about DiVincenzo's criteria for quantum computing, trapped ions sort of check all of those boxes. We have well-characterized qubits that we can prepare in states, in well-defined states very well. They have long decoherence times. We have universal set of quantum gates. In our system, we also have fully connected qubits that we can achieve all-to-all connectivity, so we can entangle any qubit with any other qubit in the system. And then we also have a few other capabilities, such as mid-circuit measurement and reset with high fidelity. And we can also do arbitrary angle unitary rotations, which is useful for a lot of cases. So at the basis of our system is our individual atoms that we ionize. So our qubits are perfectly identical. Now, of course, we put them in an environment that's not perfectly uniform, and that renders them, not perfectly identical, but it reduces the calibration. It reduces the problem to calibrating the environment and not the qubits themselves. And in the late 90s, it was realized that if you couple that you can use lasers to couple the spin and motion of ions to realize 2-qubit entanglement. And of course, this was demonstrated in the NIST group in the late 90s. Now, one paradigm for doing quantum computing with trapped ions is you have n ions in a chain, and this n ion chain will have 3 n motional modes, and then you can basically, by tuning your lasers very carefully, you can basically cause any 2 ions to be entangled while not entangling any of the other pairs. But of course, the downside of this is that you have to calibrate every gating pair, so all n-choose-2 pairs need to be calibrated. And then in addition, you want to ideally do your gates sort of adiabatically with respect to the motional mode frequencies of this crystal. And then since there are 3 n motional modes, you start to run into issues where you need to slow the gate down quite a bit, and then you're susceptible to more noise, and then it becomes quite difficult. There's been amazing work done on these long chains, but at Quantinuum, we've sort of taken an alternative approach. So the approach that we've chosen to take is this quantum charge coupled device architecture, where you do your gates on short ion crystals in dedicated interaction zones. And so this is a schematic of our H1 trap, which is the first generation ion trap. The ions are confined radially by applying RF to these dark gray RF rails here. That confines the ion sort of in this picture up and down and then out of the plane of the picture. And then all of these different colored skinny electrodes here, we apply what we call DC, just like much longer time scale dynamic voltages to confine the ions axially and then also move them around. And so basically, we're doing our gates on 4 ion crystals of 2 ytterbium-171 ions, which are our qubits, and 2 barium-138 ions, which are our coulants. And the reason for this is that in order to achieve high fidelity gates, you need to be pretty close to the motional ground state. And so in just letting the ions sit idle or moving them around, they acquire quite a bit of excitation. So you need to keep cooling them. So we can do that by applying cooling light to barium, which is very off resonant for the ytterbium ions, and so this allows us to sympathetically cool mid-circuit without having any effect on the quantum information. So we perform our gates on these short ion crystals in these blue zones in this case, and then we use transport to achieve all-to-all connectivity to move them around. And the nice thing about this is that once you can achieve high performance in one zone, you can sort of copy and replicate that performance for all of the other zones. So just as a brief kind of physical implementation, like how does this roughly work in practice? Imagine we want to implement this quantum circuit shown here, where there are 3 qubits, red, green, and blue. And so initially, the qubits are located in different positions here. We then apply some state prep lasers to initially prepare them all in the 0 state here. And then we want to do a single qubit gate on the red and green. So we'll we have single qubit lasers hitting each of these zones. We then want to do a 2-qubit gate between the red and green. So they have to physically be located in the same potential well. So we move the green over to the red, combine them into the same zone, then apply the 2-qubit beams, which in our case have a projection along the axial direction. Now we want to do a gate between red and blue. So you'll notice this is a 1D architecture and the ions can't move through each other. So first we have to do a physical swap where we reverse the order of the red and green, and then we can combine the red with the blue. And then we can do another 2-qubit gate, and then we can do a mid-circuit measurement and reset on just the green qubit, and then we can continue on in further steps of the calculation. So one thing to note here is the final orientation is different from the initial orientation. Like they're in the different order and in different locations. So there are no predefined neighbor qubits. And so the fidelities are characterized by the zones, not by the qubits. And then in addition, because we have this noisy environment, we have to track the location of qubits and any phase offsets that are accrued during a circuit so that we know what pulses to apply later on in the computation. Okay, so our universal gate set, so we have a single qubit rotation, which is done by co-propagating Raman laser beams. We have a Z rotation performed in software. We have a fully entangling 2-qubit gate, which is a Mulmer-Sorensen type interaction with some wrapper pulses that are basically single qubit pulses derived from the same lasers. And this actually gives you a phase-insensitive interaction that has the form shown here. So it gives you an I phase shift for the 0, it gives you a phase shift for the 0, 1, and 1, 0 states. And then by combining this with single qubit rotations, you can realize, for example, a C naught. So you can build up any other unitary operation from this set. But one thing that we actually find quite useful in our system is to do these parameterized angle 2-qubit gates. So, thinking about the, certain algorithms such as QFT, maybe you want to do, initially you want to do this ZZ gate with a, this theta being pi over 2, and then maybe pi over 4, pi over 8, pi over 16, et cetera. The normal way that if you only have this fully entangling gate at your disposal, then if you want to do a parameterized angle gate, what you would do is you would do 2 C naughts and you would do a Z rotation in between. So this would mean that for every time you want to do a gate that is not fully entangling, you'd have to do 2 2-qubit gates. And since these are typically the dominant errors in these systems, you want to try to minimize that as much as possible. So in our system, our native interaction is this parameterized angle 2-qubit gate. And just kind of thinking more generically about like quantum simulation, imagine you want to simulate the dynamics of some Hamiltonian that's the sum of terms that don't commute. We all know that if you exponentiate the sum of 2 matrices that don't commute, it's not equal to e to the IA times e to the IB, for example. So what you typically do is you would trotterize the Hamiltonian, you'd break it up into smaller chunks, and then sort of, as you let this f get larger and larger, the error in doing that, goes down. Of course, that only really works in practice if the error of these arbitrary angle gates decreases as you decrease the angle. And so in our system, we actually see that as we decrease the angle of entanglement, so here the pi over 2 is fully entangling, the error does go down. It does not go to 0 at 0 angle, but nevertheless, we're still encouraged by this. And just to really hammer home the importance of this, like imagine you want to do a 0.1 pi ZZ rotation. So if you did that with two fully entangling gates, you would have roughly 2 times 2e minus 3, so 4 times 10 to the minus 3 error. If you do it with a single 0.1 pi gate, you'd have about 0.8 e minus 3, so it's about 5 times better. So you get another. See, it's more than you get more than just a factor of 2 improvement. Okay, so some of the other differentiating features of this QCCD architecture. I mentioned the all-to-all connectivity. So imagine you want to entangle this top left qubit and bottom right qubit, and you just have like a 2D grid like this where you only have nearest neighbor interactions. So you can do that. You can logically swap information through the grid, but basically you would have to first do a 2-qubit gate between these two, and then these two, and then these two, and then these two. And so you need something like, say, 10 2-qubit gates for this particular case. In our case, well, we would just physically move these 2 qubits next to each other and then do a single 2-qubit gate. Now, of course, I'm sweeping under the rug here, and I'll come back to this later, that there is some error incurred by doing this transport. There's no free lunch, but the error that we get from doing this transport is sort of an order of magnitude less than the 2-qubit gate error. And so, we believe that this is a pretty competitive strategy. Yeah.
Seems like swapping really that easy. I know they use like lighter or traps, like light traps.
No, so like what we're doing, the easiest way to think of the swap is basically we're just like rotating the principal axes. So like, if you, so generally the radial confinement is going to be larger than the axial confinement. And that's just because like we set the curvature from the DC voltages to be less than the RF. But if you just ramp up that the DC voltages enough, you can basically rotate it so that now the lowest frequency direction is actually radially. And then you just reverse that in the second half, and that will actually just rotate the crystal axis 180 degrees.
How do you break the symmetry, whether it goes clockwise or counterclockwise? Everything you said right now is
I think it does have like I mean, you can. I think it does break the symmetry because I mean, it's basically like you're applying like an XY term or something like that. So whether you apply with a positive or negative sign is going to determine whether it's going to go clockwise or counterclockwise. Is that answer the? Okay. We chat more later if you still have further questions about that. Okay, so then going back to this point about the the scalable gates, we're achieving sort of state-of-the-art performance across all of our zones. And then we can also do high fidelity qubit measurement and reuse, so we can measure the quantum state of one qubit, reinitialize it to a well-defined state while with high fidelity keeping the quantum state of the other qubits intact. And then we can also do conditional logic where we can decide whether or not to do a gate on some classical variable, and this is useful for things like teleportation or other circuits like that. Okay, and then just one more slide about these the dedicated interaction zones. So in the H2 system, most of the work I'll be talking about, we have 32 qubits. So this left plot here is basically the interaction graph for 32 qubits. So each of these dots, think of as a qubit, and then there's a line connecting every pair. And so there's 496 lines on this graph here. I mean, it's a really beautiful looking graph. But imagine having to do all 496 calibrations. That would be kind of a nightmare. Whereas in our case, we just have 4 dedicated interaction zones. And so we've reduced the calibration overhead by a factor of 100 just by having these dedicated interaction zones. And then qubit reuse allows you to do some cool things where you can actually recast shallow wide circuits with fewer qubits. So you can, like, for example, the circuit here on the left is actually, if you look at like what's actually going on here, you want to measure this 4th qubit and then reset it to 0. And so you can actually do this with one fewer qubit. So you can like move the reset over here and then move the measurement to the left and then move the reset to the right here. And this allows you to, we've done this to, for example, simulate 32 spins with just 9 qubits, and also do optimization problems on 130 effective particles with just 32 qubits. And so there are some, I'll give a more concrete example at the end, but this is one of the cool things you can do with mid-circuit measurement and reset. Okay, any questions on this part before I go on to the next part? Yeah, Elizabeth? I'll come back to that later. It's 4 qubits, 4 zones with 2 qubits per zone, and then there's a bunch of others kind of living in other parts of the racetrack while those are happening. Okay, all right, so now I'll move on to the motivation for the H2 system and some of the features of the system. So this is our trap scaling roadmap Quantinuum. So the H1 system debuted kind of at the end of 2020, and it's a linear trap with 5 gate zones. Ultimately, we want to move to a more grid-style architecture where basically you do gates kind of at the centers of these streets, and then you sort ions by like doing junction transport. And then eventually we'd like to integrate optics into this structure, and then our vision for truly large systems is to then tile that into a truly large system. One thing you'll notice is like, in going from the linear to the grid, you have the complication of like, you're trying to do gates in multiple locations, parallel locations around the trap. And so the H2 trap is nice in that it's like still linear. If you're an ion moving around it, it still looks linear, but it does have parallel rows of gate zones. And so, it's sort of meant to bite off some of the technical complexity of the grid traps, but, still kind of look like a linear trap. Before I do that, let me just like point out, the H1 system has made tremendous progress, has done like a lot of really cool physics experiments, looking at topological physics, QEC, looking at the dynamics of open quantum systems, using measurement and feed forward to generate long-range entangled states. This is just a sampling. There's been a ton of other amazing work that's been done on the system. But 2D is ultimately the way to go. So if you look back at the initial proposal from NIST, they drew a 2-dimensional architecture for this QCCD, and we are actively working on this. So we had this paper in 2023 where we talk about low excitation multi-species junction transport, and then this is a series of images of an ion moving around our grid trap prototype. Of course, several technology upgrades are going to be necessary to get from 1D to something like this. I mean, one thing that's necessary, for example, is like each of these squares here has RF, and they're all connected together, and so the RF sort of you could connect them with wires on top of the trap, but that's pretty clunky. So you want to actually like connect these RF islands together inside of the trap itself. So that's one of the engineering upgrades that the H2 system has. If you think about like, we have these concentric RF rails that have to be connected together. The other thing that we do is we're using a two-dimensional MOT for our atomic source so that we can control the atomic flux optically and just sort of have this live in a separate vacuum chamber where the ovens can be on all the time. This allows us to sort of load our 32 qubit pairs in, or our 32 ytterbium barium pairs in several minutes, and we can reload individual zones in about 15 seconds. Second thing that's really important is the broadcasted electrode. So in the curves of the trap, we're not trying to do gates or anything, so we don't really care about the potential being that exquisite. So we can actually tie every third electrode together in this ABC pattern. And this, dramatically saves on the number of signals per qubit. And then, you can just convince yourself that, for example, by applying, say, a positive voltage to the A and C and a smaller voltage on the B, that you get a well every third site. And this is going to be crucial for future traps as well. So similar to the H1 trap, we're still using ytterbium-171 as our qubit, barium-138 as our coolant. We're doing operations on 4 ion chains. We're using transport to achieve all-to-all connectivity. The main differences are zooming in. Now you can see all of the electrodes here. There's 268 independent electrodes. And there are 4 gate zones on each side, which are these regions here, but we're only actually doing gates on one side, and then we can do these physical swap operations on both sides. So just to kind of summarize how we do the operations, so each of these circles here is a 2-ion crystal, so it's the ytterbium-barium pair. And we care about the order of the ions around the track as well, because we only do gates on a particular crystal orientation. So we perform gates with ytterbium on the outside and barium on the inside. And so then the order around the racetrack is always ytterbium, barium, barium, ytterbium, ytterbium, barium, barium, ytterbium, et cetera. And so, all of these are YBBY crystals. And then in the storage zones over here, we have first a YB, and then a BY, and then a YB, and then a BY, et cetera. Now, the other nice thing about the layout of this trap is that the spacing between the gate zones is 750 microns in both directions. And so in principle, if we have our beams aligned to this row of gate zones, they should also be aligned to this upper row of gate zones. Turns out that's actually very challenging to get the tolerancing exactly right, but it's good enough that we actually have to move the qubits in the top row out of the way when doing gates. Otherwise, they would get some amount of entanglement. So again, we're doing the 2 qubit gates with beams that come like this and like this, so they they interfere along the axial direction, and we choose one of the axial modes for our 2 qubit gate. And for doing single qubit gates, we would split this into two ion crystals and then move one of those into the center, and then do co-propagating Raman beams coming from this direction to do a single qubit gate. Same thing for measurement. And then we actually intentionally apply micromotion to the unmeasured ions to minimize the amount of unwanted scattering just from background scatter. And then the other thing that we're doing is the turquoise and the yellow are barium cooling sheet beams that illuminate the entire trap that allow us to do Doppler cooling while we're moving the ions around. And then we would also do sideband cooling on barium before doing gates. The load hole, there's a tiny load hole over here. So the 2D MOT, basically there's a flux of neutral atoms that go through the load hole, and then the atoms get photoionized here, and then they get transported over to this first gate zone where they get assembled into a crystal, and then we just repeat that process to build up the entire trap. So while running an actual circuit for 32 qubits, you can think of it as, it's easiest to think of it as 4 qubits, so I've put them here. And so first we'll do a single qubit. First we'll move the left ions into the center, and then we have the option to do a single qubit gate on any or all of the qubits, and then we do the same thing for the right qubits. And then we combine into the centers of the gate zones, and we do 2 qubit gates. And then we would repeat this 4 times, like once for, and then for the blue batch, for the red batch, for the purple batch. That allows us to do the gates on all of the qubits. But now we need to sort them so that maybe in the next round I want to gate some of the yellow qubits with some of the red qubits and some of the purple ones with the blue ones. So I need to do a bunch of sorting to get them into the correct order for the next round of gates. And so to do that, we do the physical swap. So first we do it within a batch, but this doesn't mix any of the batches together. And then we'll mix in sort of 1 qubit and then repeat this, and then we'll mix in more qubits and then keep doing more of these physical swaps. And you can convince yourself that if you do this enough times, you can achieve an arbitrary sorting, but it's quite slow. I forgot to mention on the 2D slide that actually, so in 2D, you actually get a square root of n enhancement of the sorting time compared to this linear case where you have to do all these physical swaps. Yeah. So for the 32 qubits, the depth one circuit time, which is like, one round of single qubit gates, one round of 2 qubit gates, and the permuting is about 50 milliseconds. Okay, so another thing that we care about a lot is memory error. So, these transport operations take quite a bit of time. And so memory error, we just refer to as anything that causes any errors that occur while the qubits are idling or transporting. And so that could be a combination of T1, T2 errors, failed transports, background gas collisions that don't destroy the trap. And so, just to describe why this is important, like imagine like I do a gate on this qubit here in this left zone, and then maybe later on gate over here and then maybe here. Then maybe eventually I want to do another single qubit gate in this zone here. If I don't carefully track the phase, then like maybe I wanted to do an X pulse here. It could very well be that I did a Y pulse or something like that. And so you need to carefully track the phase. You have to measure the phase of the SQ beams in all these zones, and then also keep track of any qubit frequency differences around the racetrack. And we do all of that in our control software. Okay, any questions on this part before I get into the benchmarking section? Okay, so thus far I've just shown you that we have a system that has 32 pairs of ytterbium and baryons, but we actually want to now do a series of experiments to benchmark it to show that it's like a useful quantum computer, because otherwise it would be like saying that you had an airplane, but if it can't take off, it's not really an airplane, right? And so we want to verify that we can actually do useful algorithms on all 32 qubits. So in classical computing, there's a hierarchy of benchmarks that you can use. So at the lowest level, you can benchmark the components of your computer, such as how fast is the processor. At a slightly higher level, you can benchmark more system level things, like how the processor interacts with the memory. But at the end of the day, what people actually care about is like how well is your computer suited to perform a particular application? Like, can it play my favorite video game or not? And that's what people ultimately care about. So similarly, in the quantum case, we can look at the failure rate of individual gates. We can look at more system level tests that involve all qubits, but these are still very specialized and not very, very useful in a practical sense. But at the end of the day, we want to look at like how well is our system performing on things that are indicative of actual algorithms that a user might run on our system. So looking at the component level, we use a thing called randomized benchmarking to assess the performance of our gates. So here, basically, we're choosing gates from the Clifford group typically, and so then you have a sequence of M gates. And so the nice thing about Clifford gates is that you can easily compute the inverse. So then you basically just apply the sequence of gates, which with no errors would basically do nothing. It would just be the identity. Of course, there are errors that cause the probability of observing the correct outcome to decay based on like the error rate and the number of qubits. And so when we do this, this is a table of our results of the different component level benchmarks. So our single qubit gates are sort of a few parts in 10 to the minus 5 in fidelity. 2 qubit gates are 1.8 times 10 to the minus 3. That's like that's our dominant error. This transport single qubit randomized benchmarking, this is, I'll get back to this in a second. This is how we quantify this memory error. This is about an order of magnitude less than the 2 qubit error. And then the state preparation and measurement is 1.6 times 10 to the minus 3. That's also a pretty dominant error, but generally, that you're not doing that as often as you're doing 2 qubit gates. And then also this measurement of reset crosstalk I mentioned, it's very good, but it's sort of at the part per million level. So now looking at a few of them in more detail. So looking at the TQRB, it's hard to see on the projector here, but the dashed lines here are for the individual zones, and then the solid line is the average of all 4 gate zones. And so this shows that we're really getting very consistent performance across the 4 gate zones. That and there are no like significant outliers or anything like that. Now this memory error test. So what we do here is, so this is kind of what I was alluding to from Elizabeth's question, is the depth 1 circuit time is, a typical quantum circuit is basically has the structure shown here. So it's like basically you have the option of doing a single qubit gate on every qubit, and then you have the option of doing a 2 qubit gate on pairs, and then you permute the qubits, and then you just keep repeating that n times. And if you do that, you can write any circuit in this form, basically. And so to measure the memory error, we take advantage of the fact that the error of the single qubit gates is very small. It's like 10 to the minus 5. It's a few 10 to the minus 5. The error of the 2 qubit gates is very large, but we can just not do them. So we can basically just run this circuit, but just don't do the 2 qubit gates, but do the permutation so that ions are transporting to random locations around the racetrack, and then we just do a single qubit randomized benchmarking experiment. And if we do that, we get a decay that's about an order of magnitude more than the normal single qubit randomized benchmarking. It also decays linearly here, which suggests that we have an incoherent scaling of errors. Because if you had, for example, epsilon1 error at depth 1 at a certain time, and then you do that n times, if you have coherent errors, they should add up quadratically. And the nice thing about this incoherent limit is that you can define an effective 2 qubit fidelity, where you basically just take your raw 2 qubit error, like this one here, and take twice the memory error, since this is defined per qubit. And then you can define an effective 2 qubit error, and then you can basically use this effective 2 qubit error to estimate the fidelity of a more complicated circuit. Okay, so now moving on to the system level benchmark. So now we want to basically, the main thing we want to show here is that if we take the component level errors, we can accurately predict the performance on these system level tests. And so for this, we chose 4 different tests, which were mainly introduced by other groups, just so that we weren't like cherry picking something that we thought our system would do really well at. So those were mirror benchmarking, quantum volume, random circuit sampling, and then also we looked at GHZ state preparation. So in mirror benchmarking, what you do is you run a circuit where each of these orange blocks here is now a random single qubit gate and then a fully entangling 2 qubit gate. And then you permute the qubits to achieve a different random ordering. And then you repeat this up to some sequence length n. And then in the second half, you just like reverse the entire thing. And then at the end, so the net effect of all of this is that it would just be the identity. And again, just so we don't bias ourselves due to state preparation and measurement, we then apply random single qubit gates at the end here to randomize the correct output, so that at the end of the day, you basically get there's one correct bit string at the end of the circuit. And then we just look at the probability of getting that bit string as a function of sequence length for different numbers of qubits. And then we see a decay, and it decays faster for more qubits, which is you would expect. For 32 qubits, there's 4 billion possible bit strings. And so, this sequence length 10 is like I think 302 qubit gates. And so we're still getting like a 35% chance of getting the correct bit string out of 4 billion possible bit strings here. The other cool thing you can do here is you can just fit this data and extract an effective 2 qubit error rate, which includes single qubit gates, 2 qubit gates, memory error. And we find that that's basically stable as we increase the number of qubits. So this is very encouraging. It says we can increase the number of qubits in the system without introducing more errors. Next thing we looked at is quantum volume. So this is a similar kind of test. This was introduced by IBM. And here we're doing arbitrary unitary operations. So each of these orange blocks here is now a random SU4 gate, which requires like 3 2 qubit gates and some SQ gates. And then we do a permutation. And quantum volume is a sort of necessarily a square circuit. So if you do it on n qubits, you have to go out to depth n. So here I'm just showing for 4 just to kind of illustrate how you would do it. But at the end of the day, we did it for 16. And more recently, we've done it for up to 20 qubits on the H1 system. So basically what you do is like you run this random circuit, and then you measure the outputs, and then you compare that with the classical expectation. And so this is not a scalable benchmark because you have to do a classical computation, but nevertheless, it's a very challenging benchmark to pass. So to assess how well you did, what you do is you arrange the ideal bit strings from least probable to most probable, and then you define define heavy outputs as those that have a probability greater than the median. And in the ideal case, in the large n limit, this goes to like I think 85%, whereas in the fully noisy, like if you were just randomly picking, you would be at 50%. So a threshold is defined at 2/3, where if you are getting a 2/3 heavy output probability with 2 sigma confidence, then you can say that you've passed the quantum volume test. And of course, it's defined exponentially, just to so that it's kind of akin to like a Moore's law type thing. And so so on the H2 system, we passed QV16 with greater than 2 sigma confidence. So that's this orange point here. And this bottom chart here basically just shows as a function of time. And sort of in 2020, we had made this promise when we were part of Honeywell that we would increase QV by a factor of 10 every year. And we've pretty much lived up to that. And so recently, the H1 system passed quantum volume 2 to the 20. So that was like a pretty big achievement. So then we also looked at random circuit sampling. So this is very similar to experiments that were done by Google and then Susongji in China in the context of quantum advantage. So to basically to do the same thing that they did, we basically did a two-dimensional circuit because they had superconducting qubits, so they had two-dimensional conductivity. So you choose like random single qubit gates and then a particular tiling pattern of 2 qubit gates, and then you compute the cross entropy benchmarking fidelity, which is basically the probability of experimentally measuring the observed bit strings. And the most important takeaway from this is that like this also allows us to extract an effective 2 qubit error, which I'll show is consistent with the component level stuff. And finally, we created a GHZ state, a 32 qubit GHZ state, which is a superposition of all zeros and all ones. And so we did this 2 different ways. First, by just the standard way that you would think about doing this, which is you do it via unitary preparation, where you do a Hadamard on 1 qubit, and then you just do C-naughts progressively to bring more qubits into the GHZ state. You can also do this adaptively, where you can use mid-circuit measurement and reset to prepare the GHZ state. And in our case, we don't have quite enough gate zones, but if you had enough gate zones that you could do all the gates in parallel, this actually allows you to generate long-range entangled states and finite circuit depth, which is kind of cool. So for the 32 qubit GHZ state, we get an 82% fidelity with the unitary preparation, and this is by measuring the populations in all zeros and all ones, and then also measuring the parity along n+1 different axes here, and that's enough to certify multipartite entanglement. Okay, so now going back to this idea of making sure that the component level and system level things are lining up. So for each of these first 3 benchmarks, we can define the average angle we can calculate the average angle of the 2 qubit gate involved in the circuit, and then from that we can compare the predicted effective 2 qubit error with that inferred from the data. And in all 3 cases, we see that they agree within the error bar. So this says we have a really good understanding of our error model, and there are no significant gaps in our understanding. Okay, so now moving on to the application levels, the application benchmarks. So here we did 4 different things that highlight different aspects of our system. So first we looked at Hamiltonian simulation. So here we simulated the dynamics of a 1D transverse field Ising model with periodic boundary conditions. And the nice thing about that is that it's exactly solvable, so you can compute the exact evolution. So we initially have j equals 0, and then we prepare an eigenstate of this second term here, the plus state, and then we turn on the j term and just watch it evolve in time. And of course, this necessarily involves trotterization, since this is a sort of an analog simulation on a digital quantum computer. And we can do it 2 different ways. We can do it basically with the native fully entangling 2 qubit gates, which is the green points. Or we can do it with the native parameterized angle gates, which is the orange points. And you can see, especially if you look at, say, this first flop here, that there's much better agreement with the orange curve than the green. And so that really highlights the advantage of using these parameterized angle gates. The second thing we looked at is holographic quantum dynamics simulation. So here, this is a general technique for sort of using mid-circuit measurement and reset to recast circuits using fewer qubits. So if you have not a very deep circuit that involves a lot of qubits, you can basically, with mid-circuit measurement and reset, you can rewrite this as a circuit that involves like t qubits but has depth L. And then in this case, this allowed us to compute correlation functions of a matrix product state evolved in a kicked Ising model for very long times. And like for this longest time point here, it's worth noting that the solid curves here are the exact like L equals infinity limit theory, so it's not actually a fit. This is the actual circuit representation of this of what it took to measure this correlation function, and each of these you can't even really see them. Each of these tiny little bars here is a 2 qubit gate. So this circuit involved 2,000 2 qubit gates, 128 mid-circuit resets, and took over 20 seconds per shot to run. Next, we did QAOA, which is a way to encode optimization problems on a quantum computer. And the punchline here is that we were actually able to see a better solution with 2 rounds of QAOA. So it's kind of like it's basically like a kind of a marriage of the adiabatic algorithm and like the variational quantum in a VQE type thing. And And so here we actually see that as we go to 2 rounds, we see improvement due to the high 2-qubit fidelity, which I think most people have sort of stopped at 1 round of QAOA in the past. And you can see that because like the data is actually below this dashed green line here, which would be the exact solution for 1 round. And then we looked at a repetition code, which is sort of half of a quantum code, so it can correct either bit or phase errors. And of course, as we go to higher distances, we see a higher logical fidelity. But the cool thing here is that we could actually go out to distance 31 with 32 qubits by using 1 qubit to measure all of the stabilizers, and it's constantly measured and reset. But this showcases a lot of the generic features you need for a QEC code, like decoding using minimum weight perfect matching and recording the syndromes. And then the other thing you can do here is that you can measure the full measure of the distance 31 fidelity and then extract subsets of say 3, 5, and all the different odd distances from the data for 31. Okay, so I'm coming to the end, and so this is the paper that we put out at the end of last year, benchmarking the system, and you can see that there's 96 authors, so not quite 100, but this is larger than like I think most of you are probably used to. And so this really highlights sort of the scale of these systems. In addition to all of the atomic physicists involved in this work, there are tons of engineering support, software engineering, optical engineering, mechanical engineering, et cetera, to really get this project across the finish line. And I'd like to convince you that I hope I convinced you so far that we're scaling high quality qubits, so we have sort of state-of-the-art specs, and we have this high fidelity mid-circuit measurement, qubit reuse, this parameterized angled 2-qubit gate. But I think perhaps most importantly, I hope that with this work we've set a new standard of transparency in the field and in benchmarking and releasing a quantum computer to the field. Okay, and so with that, I'd like to talk about briefly some very fresh data on upgrading to 56 qubits. So if you remember back from the 32 qubit picture, there are quite a few of the storage zones that were not filled. So now we've actually filled most of them in, and now we have 56 qubits, and this is actually a picture. You can kind of see like the imaging system is not quite, and there's some tilt in the imaging system so that the ions on this side are not quite in focus, but this is a picture of the 56 ytterbium-barium pairs in the trap. And we're doing benchmarking on these 56 qubits. So we've looked at the memory error and the mirror benchmarking, and we're seeing performance is consistent with the n equals 32 data. Here for n equals 56, I think there's like 10 to the 16 possible bit strings. That still kind of blows my mind that we're able to do that. We also can look at a GHZ state and measured the parity along all 56 axes and get a 62% fidelity. So we also can say we have 56 partite entanglement as well. So yeah, this is very exciting, and hopefully there'll be more to come in the next couple months on this. But yeah, we're very excited about this 56 qubit machine, because now we should really be able to start to get into the regime where we're doing things that are classically intractable, or at least very difficult. Okay, so this is the experimental team that helped make all of this possible, and the theory team. And then in my last couple of minutes, I want to just mention a few other projects that we're working on. So one question you might have is, it's like, why ytterbium? Is ytterbium the best qubit to use? And the answer is, maybe not. And so, I think a lot of the choice of ytterbium was sort of historical. Like, there had just been a ton of work done on ytterbium in the past, and we kind of just wanted to hit the ground running. A few of the issues with ytterbium, though, are one is that the gates use ultraviolet light. So we're typically, most people are doing gates at like somewhere between 355 and 370 nanometers. And, lasers of those wavelengths are just, it's hard and expensive to get high power lasers. They damage optics. And so it's really just not very favorable, especially if you want to integrate optics into the ion trap itself. It's very difficult in the UV. The other problem is high fidelity measurement is difficult as well. And so, our SPAM is 1.6 10 to the minus 3, which is like quite high, a lot higher than you'd like. And so for our next generation, we're actually thinking about using barium 137 as our qubit. And so here you can use 532 nanometers for the gate beams. And so it's really, you can get very high power, inexpensive lasers at 532. And in addition, the state preparation measurement error is quite a bit less. So we're sort of seeing, in the 10 to the -4. And I think there was a paper recently where people have done even better than this. That's kind of, I think, the future. So we're really just swapping the role of barium and ytterbium, so that barium is the qubit and ytterbium is the coolant. And then another thing that we're working on that I think is really cool. It's kind of hard to see these movies are playing here, but so people always talk about the wiring problem. Like how are you going to, like, if you want to have like a 1,000,000 qubit quantum computer, how are you going to get all the physical connections to address all of those qubits? So we had a paper on the archive, I think a couple months ago now, where we basically showed that with like between 20 and 30 DACs and switches, you can basically sort an arbitrarily large grid. So the way that this works is that basically all of these orange electrodes are broadcasted to each other, kind of similar to what I was talking about earlier in the talk with the racetrack. So for example, all of these center electrodes are connected together, and then all of these left electrodes just to the right of the junction are connected together, and then all of the ones in the vertical legs are at identical locations are connected together. And then there are these special purple electrodes in each zone called center to left-right electrodes. So now what you can do is you can basically, if you enforce a symmetry where you tie every electrode to the mirror on the opposite side, so like tie this one to this one, and these two to these two, and this one to this one, etc. And then you solve for a voltage waveform that basically moves the ion from the center to a little bit to the left or right to the center, even just like 50 microns, let's say. Basically, the only degrees of freedom you have are the only independent controls you have are these two purple electrodes. But then you get a waveform that actually, if you just then reverse like the voltages, so that if you applied, like instead of applying like say voltage A to this one and voltage B to this one, you apply voltage B to this one and voltage A to this one, that'll actually by symmetry just like make the ion, if it initially went left, it would then go right. And so that basically then allows you to basically, independent in every single zone with like only like 23 electrodes or something, basically arbitrarily decide whether the ions go left or right in each of these zones. And then combining that with global shifts, you can basically arbitrarily sort this grid, with that in mind. And so it's a bit hard to explain, but like anyway, if you're interested in that, I encourage you to check out this paper. But I think this is a huge step forward in really showing that these systems can scale with like not having like 1,000,000 like control signals. And then we're also working on integrated photonics. So we have some waveguides where we're trying to like generate the light for the different zones, and then we're also thinking about using metamaterials for like custom trap integrated optics and stuff like that. So that's also an active area of research in our group as well. And so we have we're very interested in having academic groups run stuff on our quantum computers. And so if there's any interest in that, we have a program through Oak Ridge where you can basically apply to get credits on our machine and then submit quantum circuits to run on our machine. We also have a program through Microsoft. If you're interested in that, come see me afterwards, or else check out this link here. And with that brings me to the end. And I'd like to point out that we're constantly looking for talented people to join our team. So if you're interested, I have business cards, or check out this link here, and we'd be happy to chat. So thanks for your attention, and I'm happy to take any other questions you have.
Questions, Elizabeth?
So the 2 ions per zone, is that optimal?
I mean, I don't know if it's necessarily the optimum. I mean, you could imagine like doing. I mean, you have to have some number of sympathetic coolants. So I think you want probably an even number of ions. But I mean, I think you can, like for example, like you could probably get by with like doing like 4 qubits and 2 coulomts or something like that. Maybe even 6 qubits and 2 coulombs. But the transport becomes like quite difficult. Everything that we're doing makes a lot, like especially with the junction transport, where you're doing like everything is just going like has like, you know, it's a 2-ion crystal. It just like naturally makes the most sense to do the gates as 4-ion crystals.
Other questions? Maybe I'll ask one question. So for one of the very deep circuits that you showed, there was something in parentheses about ion loss. Can you
Yeah.
comment, like, what is the loss mechanism, or how serious of a problem is that?
Yeah, so that's a really good question. So yeah, so not only do we care about ion loss, but also about the ordering around the racetrack. So like, but since we can only do gates on the specific crystal orientation, you know, we care about if we end up a circuit where like one of the gate zones is say like barium, ytterbium, barium, ytterbium, then that's a problem, because like, you know, our gate lasers are just completely off resonant for that, and that would be an issue. So one of the dominant things that actually occurs, I mean, we get some loss, like if we just load up the trap and just let it sit there and don't run a circuit, like we would get some loss, you know, probably lose like an ion every couple, maybe like 5 or 10 minutes or something like that, just somewhere in the trap. Of course, now once you start running circuits, you're doing a lot of transport. Basically, any collision that happens, I mean, we don't really have like, it's hard to like prove that this is happening, but like imagine you have like a collision while you're trying to do a swap operation or something. Even a low energy collision could, you know, reorder you. And now when you split it apart and move it somewhere else, you might get what we call a scramble, where you now have like, say, 3 ytterbiums and 1 barium in a zone or something like that. And then you know, that also causes a lot of heating, and that just causes like a billiard ball effect, where you just basically like destroy it just like, you know, creates a cascade reaction that just like dumps the entire trap. So actually, so there's a couple mitigation strategies we have for that. One is that we just do post selection. So basically we generally can run for 30 to 45 seconds and have like a decent probability of like not having any reorders or loss. And then we just, you know, we'll do spectroscopy at the beginning to verify that all the crystals are in the correct order. And we do the same thing at the end. And if they're not, then we, you know, fix it and discard all of that data. So that's like one thing that we do. Another thing that we do is that to prevent this kind of like billiard ball cascading loss is that we actually can measure barium, like while we're cooling barium, we can actually measure the counts mid-circuit. And if we detect that those are low, then we can just stop at that point. And that generally, you know, will save, like in the, you know, in the 56 qubit case, like instead of then having to reload the entire trap, which then takes like 10 minutes, we would, you know, maybe only have to reload a few ions or something like that. But no, it definitely is a big problem. And even with like, you know, really good vacuum and cryogenic, like it's still a big problem. And yeah, how we kind of, you know, ultimately, I think you're going to need to have some kind of like build that into your QEC scheme to basically just like, you know, have a reservoir of ions that you can bring in to reload if necessary. Because I think, you know, for the depths of circuits that you're going to need to do like, you know, like practical QEC experiments, you're going to be losing a lot of ions, probably.
Yeah, similar story for neutral atoms. Okay, any other questions for Stephen?
Yeah.
The DiVincenzo criteria. So when I think of the DiVincenzo criteria, I usually think that any one platform might, you know, be really, really good at 2 or 3, and another really in one being, you know, meet all of them.
Yeah.
So I wanted to ask you, do you think that there's anything to be gained from, you know, intuition from other platforms, or is this kind of ions being the ultimate platform for quantum computing?
I mean, I think in terms of DiVincenzo criteria, I mean, it definitely checks all the boxes, perhaps like more so than other platforms. I think the one place where ions suffer is that, like, say, neutral atoms have an advantage in is scalability, or just like the sheer number of qubits that you can do. Like, you know, for us, like, you know, for example, in going from 32 to 56 qubits, like it sounds really simple, but you know, you have to basically like, you know, all of the transport operations are designed with a specific number of qubits in mind. And so you have to like sort of just make all new voltage waveforms and stuff like that. So it's a pretty serious undertaking. Whereas like in a neutral atom experiment, if you want to do it from 32 to 56, you just like make more tweezer spots and now you have more qubits. yeah, I would say that like that's probably the main disadvantage. And well, and then like I think the thing that both neutral atoms and trapped ions share in common is this like atom loss phenomena, which is like, I mean, you can get leakage out of the qubit subspace in superconducting qubits, but like you don't lose qubits, right? So that's, yeah, I would say, yeah, there's more of a story than just the DiVincenzo criteria.
All right, let's go ahead and stop here, and thanks, Stephen, again.